Hello everyone and welcome back to the afternoon session, which will continue with a talk or a lecture by Professor Howard Wiseman on quantum unravelings, trajectory unravelings and adaptive measurements.
Thank you, thank you. Yeah, so I thought since I didn't quite finish this lecture yesterday, I just finish this off and then move on to what the scheduled topic for today's lecture was. So you might remember where we got up to was I posed this question about whether we can derive experimental tests that would rule out all objective pure state dynamical models for an open quantum system, including the idea of objective quantum jumps or quantum state diffusion or anything else. And I explained how my proposal for doing such a test was based on the idea of EPR steering, going back to 1935, but in particular as formalized in this paper of mine in 2007 with Steve Jones and Andrew Doherty, which formalized things in terms of a local hidden state model. So I explained then that yes, that this is my most cited paper. What I didn't say is also, but the reason I wrote this paper was precisely because I was interested in this question. So it actually all does trace back to quantum trajectories, even though that's not what this paper was about. And it took a couple of years after this to actually get around to applying the theory to what had originally motivated me to do this work. Okay, so the local hidden state model was this idea that, or local hidden state assumption is that one of the parties, Bob, the one with the quantum system, that's the one we're going to be interested in, the atom, for example, there is some actual pure state which pertains to his system, which is what these models say, but it could be unknown to him. But so the most that Alice could do is, the best she could do is if she actually knows which pure state it is that Bob has, and then when she's asked to report a measurement result, for example, the best she can do is to actually report that pure state. Or sorry, is to use that information about the pure state to come up with an answer. So other than that, we made no assumptions, but Alice, because she's a distant party, she's not actually affecting Bob's state. That's already what I said. And yes, we can construct these inequalities. So specifically here is an example of an EPR steering inequality. I'll explain how we derive it. So to begin with, this is not an EPR steering inequality. This is just a true statement about any quantum state for a qubit. Right? The sum of the squares of the block vector components is less than or equal to 1. Now, let's say now that we have another party, Alice, right? So that there is some state for Bob's system. Alice then is making these different measurements, but under the local hidden state assumption, she's not actually affecting even the possible states that Bob's systems could be in by his measurement. There is just some state. So if I take there is some real state which always obeys this, and it may be a set of different states, but if I take an ensemble average of this quantity, the first part here, when Alice is doing measurement, inverted commas, 1, A1, and conversely take the average of these two components when Alice is doing measurement 2, it's still going to be bounded above by 1, because if there is some real state there, then we can never violate this inequality. So, it doesn't matter what Alice is doing, you're not going to be able to violate that. So this ensemble average is still going to be less than or equal to 1. So just to explain exactly what a term like this means, so this is the ensemble average over Alice's reported results when she's doing, quote, measurement 1, A1. So a quantity like this means that we would, in the case where Alice is doing measurement A1 and reports a result J, okay, there's going to be some state associated with that, even if the local hidden state assumption is true. If she's following some systematic way of doing this, there will be some state associated with that, some conditioned state. If she chooses to report a particular result, that's going to be somehow correlated with what Bob's state is. So Bob can, if we repeat this experiment many times, and he bins together a whole lot of results when Alice makes measurement A1 and gets result J, and every time Bob measures sigma x, for example, then he can work out the expectation value of that sigma x. and then he can square it, and then take the ensemble average of that, averaged over all the possible results that Alice might be reporting. Okay, so this is an experimentally accessible quantity, just providing that Bob knows how to measure sigma x. And likewise, if he knows how to measure sigma y and sigma z. Okay. And if this inequality is violated, that demonstrates that there wasn't ever a pre-existing state for Bob, but that Alice's measurement results does affect the nature of the possible states that Bob holds. Okay, so if we violate this, that's a demonstration of EPR steering, which proves that there was entanglement there, but is not as strong as proving Bell non-locality. Okay, so that's the idea. So as I said, that's just an example of an EPR steering inequality, but we'll see why I chose this particular one to present in a minute. Okay, so yes, we'll see how it's relevant when we're going to apply this to the open quantum system idea. So yeah, so basically, as I said, if there is an objective pure state dynamical model, then the local hidden state assumption is true for Bob. There really is some pure state there for Bob. And so we can disprove this model if Alice can implement two different monitoring schemes on the fluorescence from the atom. So Alice is distant from Bob. She's measuring just the light emitted from that, and if they allow her to violate an EPR steering inequality. So the idea which we have is not to have some special initial conditions, but just wait for steady state where there's entanglement built up between the atom and the field that it's emitting. And then to measure the EPR steering, Bob can just choose alpha is 1 or 2, meaning to tell Alice to do A1 type of monitoring or A2 type of monitoring, and then randomly choose some time to stop the experiment and measure sigma x or sigma y or sigma z appropriately at that time, and then ask Alice essentially what her measurement result J is. But that measurement result, I mean, obviously she's been measuring, doing some measurement up to that time. She's in a sense got an infinite amount of data. You can't beat an experiment, when you've got an infinite amount of data, but we don't need that because for Alice, what's important is just what is the conditioned state that she thinks she's got conditioned on what she's seen so far. And essentially that's what she should report to Bob. So Bob can then bin different conditioned states. You could take your block sphere and divide it up into little cubes or whatever, and so you say you've got 10,000 of them. Well, then you've got 10,000 bins, but you can still do this this sort of process. And there's probably shortcuts as well, but in principle, this is how it could work. So Bob then just stores his data, in other words, the results of these measurements that he's making in different files, depending on which measurement Alice is doing and which conditioned state she said she had in that particular run, and then he can work out those quantities. Okay, so what monitoring schemes should Alice use for these? Well, at present, for this example of a fluorescing atom, and again, here's a cartoon with a supposedly parabolic mirror so that we can get all of the light coming out this way, or as much as we can. We really do care about efficiency, as we'll see. And so homodyne measurement is a good choice because we can do homodyne measurement generally more efficiently than at least fast detection of photons. So then, what's our choice? Well, our choice is that we can use different phases of the local oscillator, and I put up some pictures of that before. You get different trajectories depending on that phase, and Benjamin also put up pictures showing these differences. So that's essentially the choice that Alice has, and yeah, I think I already said that. Okay, so here's a picture of the different sorts of states which we get. So this is a relatively strong driving limit of resonance fluorescence of a two-levered atom. So I've got spontaneous emission and I've got driving. This is in an interaction frame. So that's my Hamiltonian, just looks like this. And this is an equal area projection of the Bloch sphere. So I'm just taking the Bloch sphere and unwrapping it and sort of looking from a distance, and that gives you an equal area projection. So this is the case of perfect efficiency detection. So it's completely pure, which is why I can just look at what it looks like on the surface of the Bloch sphere. If Alice does homodyne X detection, I should say, yeah, these are pictures from one of my very first papers on quantum trajectories, but I've always liked this system, and so yeah, I haven't grown tired of it. I think it's fascinating the way this works. So with homodyne X measurement, which corresponds to a phase of 0, the Bob's conditioned state tends to localize, as you see, around very approximately around 0 and pi for the azimuthal angle, which means that these are states close to sigma x being plus or minus 1. Whereas if Alice does homodyne Y measurement, which corresponds to a phase of pi over 2, then the states are completely different from that. They actually, so there's a bit of a scatter here because that's transient. In the long run, it literally just circles around the great circle where x equals 0. So it's as different as possible as you could be from x eigenstates, and in fact, they're states where the average of y squared plus the average of z squared is equal to 1. So obviously, in this case, the average, if we're exactly this, the average of x squared would be equal to 1 as well. So this suggests that this is exactly the sort of scheme which we could apply our inequality to. So here's the inequality again. And we are going to now use A1 as obviously being Alice doing X homodyne and A2 as Alice doing Y homodyne, and ask the question, can we violate this inequality? Well, definitely we can if we do 100% efficient detection. So the question is, will we violate it with less than 100% efficient detection? And so this was when I eventually got around to doing this work with Jay Gambetta back in 2012. And we showed that, yes, you could violate it if you got an efficiency greater than about 73%. So that's still hard because you have to collect all that light, but it's not like absurdly high. So there's possibilities. But could we do better? Is 73%, does it really have to be that high? Well, one thing which we showed, so this is with a student I had a little bit later, Shakib Darianush. We showed that if you only look at homodyne detection, or in fact any sort of diffusive detection, homodyne, heterodyne, etc., of any type, if all your channel, it doesn't matter how many Lindblad operators you have, doesn't matter what the system Hamiltonian is, if all of your channels can at most be monitored with 50% efficiency, then you will never be able to demonstrate EPR steering. So that's a pretty powerful no-go theorem that says with diffusive type measurements, there's this real bound. But we also showed in this paper that well, we can, so there's a no-go theorem, but we can say go no further no-go theorem because we can put in something which is not diffusion, in other words, quantum jumps. And maybe I won't go through the details of we consider a different scheme for this. I'll just say it involves adaptive unravelings, which I'll talk about soon. So it's a much more complicated type of system, but nevertheless, it's conceivable. And in this case, we find a very different result that is possible to show EPR steering with an efficiency as low as 37%. Okay. And just to give you an idea of how low that is, that's a smaller percentage than the percentage of words in this title that are quantum. Okay. And it's a different inequality as well. It's also a more complicated inequality. But yeah, for time, the interest of time, I won't go through the details of that. Okay, so to summarize what I talked about mostly yesterday, well, in fact, this slide is it's all what I talked about yesterday was the brief history of quantum trajectory theory, starting with objective pure state dynamical models back in the 1910s with Einstein and Bohr, the long night where quantum jumps didn't get talked about much, and then how he was gradually resurrected in the 1980s and early 1990s. Yeah, I won't go through all that. Stochastic master equations, unification, Pierre talked about that. Moving on to what I just talked about finished the story of this morning, this afternoon rather. Yeah, so in the modern understanding of quantum jump theory and more generally quantum trajectory theory, it is understood that objective pure state dynamical models for general open quantum systems are false because different distant detections lead to different unravelings. But as I said, this has never actually been rigorously proven, but we proposed this quite a long time ago now, proposed experiments to do this, and yeah, I won't reiterate those things which you've just heard. Okay, so I've got one more slide on this. Oh, okay, well, strictly two more slides on this talk. So I've called this Contrived Questions for Future Lectures or Work, which is basically just advertising things I want to advertise, but then I'll open for questions. So will experimentalists try to disprove objective pure state dynamical models? Hopefully. Will I explain more about adaptive unravelings? Yes, actually today rather than tomorrow. Okay, so here's a question that I talked about, especially in the context of Balabkin's contribution, that we can think of quantum trajectories as a quantization of classical filtering theory, as the term is used in control theory. And if you know about filtering theory, then you may also know about classical smoothing theory, and you may wonder, can we also quantize that theory? And yes, I'll talk about that next week. Okay, a bit of a smiley one here. You might ask the question, given that I detected a photon by direct detection, what would have happened if I'd been doing homodyne detection? You probably wouldn't ask that question, but it's the sort of question that I asked. If you're interested in that, then I recommend you to see my student Ingita Banerjee's poster and a short talk next week. Where is Ingita? There we go, yep. Cool. Right, another question that you probably would not think to ask at this point is, can a photon spend a negative amount of time in an atom cloud? Especially because you jumps. Well, again, if you're curious, I snuck in an extra poster this morning, so you can go and look at that and ask me about that. And it does have something to do with quantum jumps, just to reassure you. And finally, I will just advertise, so another collaborator of mine, Ariya Chantasi, also has a talk on a different way of formulating the stochastic master equation. That will be next week. Okay, so I guess would be appropriate to pause for any genuine questions at this point before I go into the next lecture. I guess the chair, unless the chair, sorry, I mean, up to the chair, I guess. Should I pause now or? Yeah, okay. Okay. No, simple is genuine, yes. Complicated is often not genuine.
So, if I understand, what you present is the two-dimensional.
Yes.
So, what about the case of continuous variable, and what would be the constraint on efficiency?
Yeah, so I guess there are lots of questions you could ask. You could say, would it help to have higher dimensions? Would that also help you to get a lower efficiency? Yeah, it's wide open. I mean, I don't think anybody's done any work on it apart from these couple of papers that I've presented. But I will just say that this theorem, and we actually have a more powerful result than this, but this is the one that's simplest to state. This limitation on the ability of diffusive measurements like homodyne or heterodyne is completely universal. It doesn't matter what the dimension of your system is or how many channels you're measuring. If your efficiency is, you need to have at least one efficiency higher than 50% to have any chance of being able to do EPR steering. So that's a general theorem which applies to continuous variable systems. Yes. So when we say efficiency, that's the whole channel efficiency, if you like, from the source to the photocurrent, the homodyne photocurrent.
Do I understand correctly that the violation comes from the two directions you choose to measure are non-commuting? And so
okay, so yeah, I want to stress that Alice is not doing anything different to Bob's system in the sense that there is not a different coupling. We have a fixed coupling which just leads to spontaneous emission of the light. So the different non-commuting things that Alice is doing are the different choices of measurement on the field. So yes, you could say that that's where the non-commuting is. So choosing to measure the X quadrature of the field is different from choosing to measure the Y quadrature of the field. And so yes, that's why they're incompatible, yes. And that's actually a quick way to see why, if your efficiencies are less than 50%, then in fact you can measure both, you could in principle measure both quadratures at the same time with 50% efficiency. And so that's a quick way to understand why you do need that 50%, more than 50% for the quantum diffusion case.
Okay, thanks.
Yep. Yeah.
Do you think a similar result could be derived for jump?
You mean a bound?
A bound on the efficiency?
Well, not a similar one in the sense that we know it's not 50%.
Yeah, so my follow-up question is it fair to compare both efficiency? Because are they like homogeneous? You know, one is square root in the SME for the diffusive, one is...
Well, I mean, in the sense that if you just thought of it all as being lost in a channel prior to your being able to detect, then it's a fair game, right? You've got...
So one has the square root and not the other?
No, but forget about the mathematics. Just let's say I have a loss channel where I have 50% loss. Then if you're only doing diffusive measurements, you have no hope of doing EPR steering. But if you can do quantum jumps, then you can.
Okay, indeed. Thank you.
Any more questions? If not, I think we can...
Okay, great. So move on to part 2 is what happened to the IT person. Okay, I'll see if I can get it. Yeah, here we go. It looks like that might work. Anybody know how to get back to full screen? Yep, great. Okay, so yeah, so this is now the topic of today's lecture. And again, I've got, well, I don't have a co-presenter this time, but I've singled out 2 names, even though I'm going to be talking about a whole lot of things, 2 names of people who've worked relatively recently with me on a part of this work that I'll get to at the end. So yes, so Raiza Karasik and Prahlad Basashki. So the topic is adaptive measurements for profit and pleasure. And these 2 are associated with the pleasure part, and I'll explain what I mean by that as we go. Okay, so I want to begin by explaining this notion of adaptive measurements. So yeah, I went back to some quite old slides when I put together the tutorials for this talk, which might have been obvious. And I spent quite a lot of time updating them. But yes, old enough that it was back when I was consciously advertising the fact that I had a new book out with Cambridge with my old supervisor, Jared Milburn. So anyway, I decided to leave it there anyway. So yes, this book called Quantum Measurement and Control. And so when people, see that measurement and control, they most naturally think quantum feedback. Okay, well, quantum measurement control, feedback. Because this is, yes, the most obvious way to combine the ideas of measurement and control. And the aim of that is typically to change the average system evolution to achieve something. And so here's, I think this is, Klaus put up this example, a beautiful example of an experiment in quantum feedback from Serge Haroche's group. So that's just to illustrate that. Okay, so feedback is a non-trivial thing even classically, so there's a huge classical literature on that. But there's another way that we can combine measurement and control, which I would distinguish from feedback, and that's what I call adaptive measurements. And what we're doing in this case is controlling future measurements on the basis of the results of past ones, not with the aim of changing the average system evolution. So if we want to be really strict about it, we could even say we're going to insist that the average system evolution remains exactly unchanged. But the aim of the changing the measurement is to obtain better data. And so that's the point of that. So I think this is interesting because classically, if we have perfect measurements, then this is a non-problem. Because basically there's no sense of controlling future measurements, changing future measurements. If you've got a measurement and it's as good as you can make it, then there's no reason to change it, right? We don't, the concept of choice of measurement in classical systems doesn't really exist, right? If we can make a measurement, if we can make one, we just choose the best measurement we have that gets as much information, this is the idealization of classical, obviously. Gets all the information, we just use that good measurement all the time, there's no reason to change. But in quantum mechanics, the choice of which measurement to make is a real choice because of incompatibility, etc. And so I think adaptive measurements is particularly interesting in the quantum case in a way that it's not so in the classical case. So that's why I wanted to give a whole lecture on the topic. And I guess also because it's something that I've sort of specialized in. And so, there's a lot of things that I can say. So, right, profit and pleasure. So I have a very low bar for profit. Profit means a theory which can be applied in an experiment which can be published in a reasonably high impact journal. So I don't mean literal profit, okay? Although I will say something at the very end. So that's what I mean by profit, is something where we can actually, at least conceivably, apply this and with real in real situations and see the effects. The pleasure part is something which I'll get to in the second, this part of the talk, is a much more theoretical question. It's basically one where I'm going to, everything which I told you yesterday about, real measurements we have to deal with, inefficiency, blah, 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 blah. I'm just going to throw that out of the window and say, okay, let's assume we can do everything perfectly and and ask this question, which I guess probably easiest to explain when I get to it. Okay, so before that, I want to explain in a bit more detail formally how we would define this concept of adaptive measurements. And so I am hoping that you have been presented with a general theory of quantum measurements. Am I right? The people who've been here all since last week? Okay, great, all right. So so I'm even simplifying here and not considering the most general sort of measurements. I'm going to assume measurements which can be described by what I call measurement operators. So these are not POVM. So basically I'm going to consider measurements which preserve the purity of the state, just for simplicity, okay? So a measurement, this I don't know what it is, fractor M, is a set of ordered pairs of results and measurement operators associated with those results. And the way the measurement operators work is that if I get result R, then the new conditioned state is MR rho MR dagger. And that thing also gives us the probability. So the trace of this unnormalized state is the probability of that. And we have this completeness relation on the measurement operators to preserve probability. Okay, I'll also introduce this T in this color green to be the total unconditioned, which is the map which takes me to the unconditioned measurement, post-measurement state, and that's a CP-TP map. Everyone knows what that is. Okay, so one more concept I'll introduce here is the idea of a complete measurement. A complete measurement is one which has a rank 1 measurement followed by, which can be followed by a unitary, for example. Okay, why do I call that complete? Because once I've made it, the system state is completely determined by the result of the measurement. Okay, so any information, there's no more information to be gained by making any future measurements in that case. So we can say the measurement is complete. If you want, go and get a new system if you want, but there's nothing more to be done here. And so obviously the complement of that is the set of incomplete measurements, where it does make sense to do another measurement to maybe try to get more information. Okay? So in this situation where one does have incomplete measurements, so then one can have the ability to perform a sequence of incomplete measurements. And if there are restrictions on the class of each measurement, but still some choice as to what measurement to make, then the optimal choice of what to do second is going to depend on the result of the first measurement, and so on and so forth, right down the line. So this is the concept of an adaptive measurement in sort of formal terms. So in particular, if we could say that this is purely an adaptive measurement, if we place the restriction on the measurement in step n, that the CPTP map for that is fixed. In other words, whatever choice we can make for the measurement to do at step n, it can't change the average evolution of the system. So in this situation, this is a purely adaptive measurement. The system at the end of the time is completely, averaged over the results, doesn't depend on what I chose to measure, okay? But the quality of the information which I got does or can, right? So it makes sense. So this is why I emphasize this as distinct from feedback, is that you're making absolutely no difference on average to the system state, but you are achieving something by this control, which is to get better information. Okay, so yeah, so getting on to what is this actually useful for? What are some examples? And I've sort of split this up into sort of a rank order of more, from less interesting to more interesting, but they're all sort of interesting. So I think the very earliest quantum example that I'm aware of is what I proposed in 1995, which is a quantum trajectory based on quantum trajectory theory of making a single shot estimation of a fixed phase on a coherent state, okay? So you have a coherent state of unknown phase and you want to know what that phase is. How best can you do it? Well, the standard way of doing it is to do heterodyne detection. But if you actually do adaptive detection, and this is a cartoon which Hideo Nobuchi produced, which I've just stolen, because being a theorist, I was always too lazy to actually draw anything like this. The idea is, so the red is the bit of the signal which hasn't been measured yet. And so as it comes along, we measure a little bit of it. That's black. That gives us an estimate of the phase. I can use that very rough estimate to control the phase of the local oscillator here so that it's better suited for getting information about the next part of the pulse. And then likewise, I use both of these bits of information to update my estimate of the phase and keep going until I've made a better estimate than I otherwise would be able to of the phase of this system. And so the theory was that you could get for a coherent state, you could do twice, you can halve the variance or mean square error in your estimate of the phase. And the experiment was performed in the group of Hideo Nobuchi, and they measured something fairly close to that. Along the same lines, but not with a fixed phase, but rather we can consider a coherent beam with a phase which is continually moving in time. So Klaus talked this morning about this exact problem of trying to estimate a parameter which is changing in time. And so, yeah, we were able to do some theory about that, and you get a different sort of reduction, but you still get a reduction in compared to standard theory. And again, an experiment was performed a bit later, seeing something close to that as well. All right, moving away from continuous measurement. So this is not really quantum trajectories in the sense of describable by diffusion or jump processes. This is just simply a number of photons. I thought about skipping this completely, but then I decided I would put it up because one thing, again, to comment on Klaus's talk, so Klaus did a lot of stuff with Fisher information, and I think said something like, oh golly, which way around is it? Would you agree with that, Klaus? Yes. And so this is an excellent, okay, so the Kramer-Rao bound, which Klaus mentioned, is this. And it is an excellent heuristic to say that they're equal in many, many situations. But there are a few special situations where it's not. And in particular, when you try to push to the extreme of getting as much information, trying to make as good an estimate with some particular constraint. And so in this problem, we're looking at the constraint of estimating a phase in an interferometer. So this is an unknown phase here, where we're fixing the number of times a photon can go through that interferometer. And there are sort of resource theoretic reasons why this is a sensible thing to do. And in that particular case, if you just ask the question, well, given that it goes through the interferometer n times, what's the biggest Fisher information I can get? And the answer is n, and that would suggest that if you thought you could make this equal, that would be 1 over n squared. So it turns out that that's not true. Okay, in this extreme case, the limit, I'll say, asymptotically, it's actually that, which I've simplified to 10 over n squared. So that's what we call the Heisenberg limit, not 1 over squared, but approximately 10 over n squared. And so that's sort of significant because with the adaptive scheme we got, which we came up with in this paper, we got an estimate of a mean square error scaling like 15 over n squared, which doesn't sound very impressive if you compare it to 1 over n squared, but is not far off 10 over n squared, right, which is the Heisenberg limit. And the point is, and it performed better than the best known non-adaptive scheme, which is one that we also came up with. We tried very hard to find the best non-adaptive scheme. And so yes, we get a significant difference with that. So you can do better, right? So these are examples of doing things better. But it's more interesting if you can do things much better, meaning a different scaling. Okay, and so to do that, typically you have to do not just use adaptive measurements, but also use some form of non-classicality, such as squeeze states or entanglement. And I won't go through the details here, but here's an example of homodine tracking, so diffusing phase on squeeze states. We find a different scaling law in comparing adaptive to standard technique like heterodyne detection. And there was an experiment done in the Kira Furusawa's group where they didn't measure a difference in scaling law because that would require extremely high squeezing, but they did see something significantly below the standard limit. Is that all that's there? Okay. And then moving on to doing some things perfectly now. Surprisingly, there are things that where you can work out the quantum. So maybe I'll put up this case. Like here we have the Heisenberg limit, which says you can do it this well. It is possible to achieve that, but not with adaptive measurements where you measure photons one by one and then change what you're doing for measuring the next photon. You would have to do an entangled measurement over a whole bunch of photons. Okay? So that can't be achieved by adaptive measurement. But there are some things where it's not obvious, where you just do the theory completely generally. I guess a bit like Klaus's case, where you work out the Fisher information of an atom, sending all of its light out, and then you find you can achieve it just by counting the photons. Incredibly, it's so simple. So there are sometimes we're lucky like this. So the problem of discriminating between a vacuum and a coherent state, for example, was, so I shouldn't say that was the first example of an adaptive measurement, because of course, I'm forgetting that way back in 1973, Dolinar, in a report in IBM, came up with a way of doing an adaptive measurement to distinguish between these optimally, like as well as quantum mechanics could allow at all. Again, when I went through my old slides at that time, probably 10 or 15 years ago, I was still advertising this paper as being an experimental realization of this. And I guess for anyone who doesn't know, this is definitely should not be cited as an experiment which actually realized this. So this has not been done yet, even though the paper hasn't been withdrawn, but there we go. A similar example is where you have a bunch of non-orthogonal states. It's either all one state or all the other states, can be optimally distinguished between those. And it turns out, again, you can attain exactly the best that quantum mechanics allow adaptive measurement, and we did an experiment on that. Okay, another example, and I think I really won't go through the details on this, but again, it turns out with this same sort of counting of multipasses, if you allow yourself entanglement, then you can actually achieve so maybe what I said earlier was not quite right. If you allow yourself entanglement here, then with adaptive measurement, you can do as well as quantum mechanics allows. We did this experimentally for 3 photon passes, which was an entangled state of 2 photons, one of which went twice through the phase shifter, and the other one only went once through the phase shifter. And then we do an change the measurement on the second photon based on the result of the where the first photon is detected, and we got close to the best possible. This is not a noon state entanglement. Yeah, so good question, because a noon state is, yeah, if you just maximize the Fisher information, right, to get this to go like 1 over n squared, you want to create a noon state. And so a lot of people put a lot of effort into creating a noon state. But that's not the state that gives you the best phase estimate. It is the state which maximizes the Fisher information, but not the state which gives you the best phase estimate. So this was using a different state, like a state which had never been produced before for 2 photons. Yeah, and it worked pretty well. Yeah, so thanks for the question. Right, another thing which surprisingly you can do perfectly with adaptive measurement is to do a phase measurement if you know your signal is restricted to the vacuum and single photon subspace. And again, I think yeah, well, maybe I'll briefly say, so basically the best you could do, so you're not going to be able to get a very much information about a phase if you've only got at most 1 photon, right? We don't expect the estimate to be accurate, right? There's almost nothing there. There's almost no light there. But you can still ask the question, how close is it? And we can exactly quantify how close it is, and we can show that you can do better. So basically, if you just randomly pick some homodyne angle and measure along that and use that to estimate your phase, then it's essentially equivalent to having a perfect measurement, which we'd be projecting onto a phase state 80% of the time, and 20% of the time just having a completely random result. Again, but this perfect measurement itself is a very broad distribution. It's like a cosine squared distribution. Whereas if you do heterodyne, you do better. It's like having an 88% perfect measurement. But if you do it adaptively, it can be 100% as good as quantum mechanics allows. And so there was an experiment done in using superconducting. I guess this is the first one coming up. All the other experiments I've talked about with using optics. This is using superconducting system. And so yes, this is the adaptive measurement being done here. So essentially you get the JPA is the Josephson parametric amplifier, which I think Benjamin talked about. You can choose which quadrature you're measuring in the JPA by changing something in it. And so the adaptiveness is you get the signal out of that, you process it, you send it back and change which quadrature you're measuring and do that continuously. And this way you can realize an adaptive measurement here. And again, they wasn't anywhere close to actually being perfect, but it was significantly below what could have been achieved by the best possible standard way of doing this experiment. And finally, I want to talk about doing some of the things uniquely. So in other words, questions which don't really even make sense to ask unless you're thinking about adaptive measurements, or for which the answer would be trivially like, no, that's not going to be possible, right? Unless you do things adaptively. And so here, my first example is actually measurement-based quantum computing. So this is not an experiment I was involved in any way. Well, okay, so this was just the first experiment again, but now what's changed since the last time I gave a talk about this is we really can talk about profit now, right? In that there are companies, I don't know if they're profitable companies, but at least they're companies with a lot of investment, which are implementing or trying to implement quantum computers based on this idea. So I guess, yeah, the point is you build up some entangled state, you make measurement on 1 qubit, depending on what result you get, that changes the measurement you make on the next qubit, and so on and so forth. So you can think of measurement-based quantum computing is just one great big adaptive measurement. That's what it is. And classically, of course, this makes no sense. Like classically, you can't do computation by preparing a state and making measurements, even if those measurements depend on, the measurements you made on other systems. It's like, yeah, it just doesn't work. But in quantum mechanics, this does. And I guess the point is that yes, on average, the system state after you finish the computation is all gone. Right? You've measured all your qubits. If it's optics, which is what they typically are, there's just nothing left, right? You've absorbed all of it. So your average evolution, the aim of this is not to change the average evolution of anything. It's just to get the information, which is the computation result that you want. And then finally, and so this is where I'm going to get into finally the second half of my talk, the bit which is for pleasure, is this idea of tracking an open quantum system with a finite classical memory. So here's a cartoon of this. I know it's, so I have a system with coupled to some number of baths. I'm just going to imagine that there's some detector which I put out there, so I call it a detector singular. Of course, in reality, it might be multiple detectors, but I don't want to restrict in any sense the way I might be measuring the bath here. These are detectors this is a detector that's going to click, in a sense. It's going to have discrete outputs, so that's what this DNT, and that goes to classical memory. And basically whenever I get some signal coming out of my detector, the idea of tracking, right, so let me step back. This box here, this purple box, is a finite classical memory. And by finite, I'm talking about trying to make it really finite. So it might have only a few possible states that it could be in, right? So it's a finite state machine. And basically, when it gets some signal from the detector, it's going to update its state from like state 3 to state 5. Something like that. And then it's also going to send based on whatever state it's in, it's going to tell the detector, okay, now detector, reset yourself into this configuration appropriate to the state that I'm now in, this measurement. So some particular state from between 1 and k for some finite k, and yeah, reset yourself. So this is why it's adaptive, clearly, because of this loop here. But again, it's not changing the average evolution of the system. The only aim of this, making this adaptive, is to try to keep track of so this is the crucial thing. The point of what this classical memory is supposed to be doing is knowing what the state of the quantum system is. Okay? So each state of the classical machine is supposed to correspond to a different pure state, because I'm going to assume everything is perfect, pure state of the monitored system, and there are only finitely many possible pure state that it's in. Okay, so that's the idea. So this was originally proposed in this theory paper by me and Rajat, and then I've done some more recent work with Prahlad Brashasky. Okay, and as I said, but this really is this is the sort of thing you can only do uniquely, but as I said, because I'm assuming everything's so perfect here, this is really just for the theoretical pleasure of thinking about this problem. So here's a way I can phrase the question to try to make it sound interesting. How big a brain does it take to track an open quantum system? How much memory do you need? Okay, so this is where I'm going to link back. So I think I talked about this in yesterday's lecture, that it was Einstein who first introduced actual rate equations for quantum jumps. And so he wrote down equations like this in slightly modernized notation about the probability of the system jumping from state Zn to state Zm, being given by some rate, and he wrote down these famous equations for what those rates look like. If you were going up in energy, then actually, no, the other way down. If you're going down in energy, it's 1 plus the mean number of thermal photons at that frequency. If you're going up, it's proportional to the number. Yeah, and that's that definition there. Okay, so this dynamics, so I don't think he wrote down exactly this equation, but it corresponds to a classical master equation. Okay, so for those who don't know, the term master equation comes from classical mathematics or physics, and yeah, that taken over into the quantum case. So this was originally what people meant by a master equation. It was an equation like this for probabilities. And so this is just the generic, what a generic probability equation looks like for a discrete system. Okay, I have these rates kappa mn, and that's the probability being in state M decreases if I have because of jumps out of that, and increases because of jumps into that. So I guess this kappa mn must be the probability of jumping from n into m. Yeah, that would work. Okay, and yeah, so this equation for Einstein's, this was the point of his paper. If you choose these rates, then you get a Boltzmann distribution in a steady state for the atomic populations. Okay, so I sort of stress this because I want you to look at this equation, because you'll see another equation that looks a bit like it later, but which is not the same. Okay, yeah, so I think I talked about this already. I put up these. So yeah, in their way of thinking about these were objective stochastic events into the radiation bath. So in this case, if we can keep track of these events, then we could clearly know which state the atom is in, right? That's a pretty obvious thing to say, right? So if I can treat the atom as having only finitely many levels, say d levels, then how big would my brain have to be? Well, it would only have to have d states, right? That was all I would need to keep track of the state of this quantum system, because it's one of these d levels, right? It's pretty straightforward. So that's essentially, so even though we're talking about quantum jumps, it's really all a classical theory. And in the classical case, if I have a d level system, I only need d states in my brain, d states in my classical machine to keep track of that. Okay, so now moving from the old quantum theory of quantum jumps to the new quantum theory. So yeah, I mean, a lot of people have talked about this already, but just to go through it very quickly, if treating everything pure, to make it simple, keep it pure and simple. If I have an environment in a pure state and a system in a pure state and they interact, then typically the global state that comes out is going to be entangled. And so when I trace over the environment, I will get a mixed system state coming out at some time t. And if I can make the Born-Markov approximation, then I can write down a good approximation to that evolution as being for this mixed state as according to this master equation here. So again, a quantum master equation now. Okay, but then as I talked about, that if this is true, if this is how I've derived my master equation, then it's also the case that I can actually monitor the bath or measure the bath in order to monitor the system and get information without invalidating the master equation. And in that case, I can collapse my system to a pure conditioned state, which on average reproduces the master equation evolution. So all this stuff you've heard before. Have you seen this? Have you seen this equations that look like this before? No one's jumping up and down. All I wanted to do here is, in case nobody's pointed out, this is just like really easy to see, like how do you get quantum jumps out of a master equation? So there's my master equation, but I'm going to write it expanded to order dt. And then I'm just going to collect some terms. So basically I'm going to collect this term is going to be one of the terms of, it's going to be this term here. And everything else, so this plus all these other terms of dt, I'm going to collect like this. And when I do that, I can rewrite this P1 is just, where to go? Right, it's just this, okay? So I take P1, obviously that cancels out. I read dt times c is going to give me the dt times c rho c dagger, right, when I take the ket and the bra. So that's that term there. Everything else here is, if I start with the pure state, I should have said, if I start with rho t being a pure state, then I can write, then all the other terms I get, you know, second order in dt terms, and I just throw them away. But I can write this, this state after one time step evolution as a mixture of two quantum states, one of which is completely different from the initial state, right? Because the initial state was psi, but here I've multiplied by c. And it's a very small term because it gets multiplied by root dt, which means dt itself when it's multiplied out. And the other, which is hardly different from the initial state at all, because it's 1 minus terms of order dt times the initial state. And so I can naturally think of this as, well, after one time step, there are two things which could have happened. Either the system has undergone a quantum jump, and so that's this term here, which is of order dt. So that's a very rare event. It happens with probability of order dt, which is exactly what you'd expect for something which happens with a finite rate in a time dt. And the other probability happens almost all the time, so 1 minus the probability of a jump. And in that case, you have smooth evolution. Right? So that's how we can unravel the master equation in this very simple terms. We get that if we have a detection, the interpretation is that the events 1 are the detections, and the event 0 is not a detection. And when I get a detection, I get a jump, right? The system is completely changed. And if I don't get a detection, then I have smooth evolution. Smooth, but not unitary because of this term here. Okay. So here, right, so let's contrast this with Einstein and Bohr's theory of jumps. So obviously it has in common the fact that you have jumps, the system state can change suddenly, and they happen at a finite rate. But for the general theory, right, if I just write down some completely general Hamiltonian, completely general Lindblad operator here, many of the properties of Einstein and Bohr's jumps do not apply. So in particular, the post-jump state can depend on the pre-jump state. So it might, though in the Einstein case, if I tell you that a photon of this energy has been emitted, well, the system must have jumped to the state below that energy gap. If all the energy gaps are non-degenerate, if you know the jump, then you know what the final state is. But in general, that's not the case. It's not even the case that the post-jump state is necessarily orthogonal to the pre-jump state. It's not like jumping between distinct energy levels as in Einstein and Bohr's. And even with no jump, right, in the Einstein-Bohr theory, if you don't jump, then you just stay in the energy level you begin. But in general, for a general master equation, that's not the case. You're going to move around. So in general, so this is similar to the picture which Pierre put up yesterday. You have some picture of the state space of your system. So in this case, I'm taking it to be pure, so it's the block sphere. And the system, undergoes some smooth motion interspersed with jumps to somewhere else in this space, and then it does some more smooth motion, and then it does some other notion. But yeah, so in general, this is the typical picture of what you get if you just do a jump unraveling. Is that the condition state is going to explore some manifold within the Hilbert space. Okay, so it might, for example, explore over time the entire block sphere. And the possible pure states I have would have to be described by an integral description like this. So very unlike, so even for finite dimensional system. So here, this picture, right, a two-dimensional system, there are infinitely many possible states that the system could be in at some time. So strictly speaking, you would require a classical memory of infinite size to keep track of which pure state the system is in. Obviously, for particular, systems, this may not be the case, but generically, right, you need a lot of classical memory to keep track of the state of even a finite dimensional quantum system. So then that raises the question, can we control the way the system jumps? Again, always emphasizing this is without changing the average evolution. So we're not doing feedback on the system, we're just changing the way we get information about the system in order to restrict it to finitely many states. Okay. So yeah, so this is, as I said, an example of adaptive monitoring. Yeah, so we're not changing the average system dynamics. So yeah, I think I showed a picture. I showed exactly this picture in yesterday's talk. This idea that what can you do? To get a different information is to interfere the light coming from your system with a local oscillator. And the idea of adaptive measurement is to take the last click, use that, process that in the appropriate way to change the properties of this local oscillator before the next click. Okay? And that's the general idea of adaptive unraveling. Okay. So that's the question, right? Can we do this? Can we do this adaptive unraveling? Well, the answer is yes, but it turns out the way we solve this is to sort of completely ignore all those details of the adaptive and use a theorem, well, I'll get to in a minute, that was proven by myself and Okay, so let's get to some mathematics though. We're going to restrict to ergodic master equations, so ones where there is some unique steady state. And I'm going to talk about, consider an ensemble of if there exists positive weights so that I can write the rho steady state as a mixture of those pure states. Okay, but this is a crucial point that saying that a set of pure states represents rho is not the same as saying that that set of pure states is physically realizable. Okay, so that's a technical term, physically realizable. What I mean in this context is that there exists a way, which could be adaptive, right, to monitor the bath such that for all long times the system is in one of these states. Yep. So it will equal phi k for some k. So there's a difference between just being able to represent rho and actually being physically realizable, actually knowing at all times that it is one of these states. So as I said, so we proved this theorem back in 2001 that says that an ensemble of pure states is physically realizable if there exist rates such that this equation is satisfied. So this is the one, this is why I said to think about that classical master equation before. The classical master equation, there was like a P dot J here, if you like, and it was a sum over these, and there were probabilities here. So it's not the same equation, but it clearly has, it's reminiscent of it. Now, I don't have enough time to explain where this equation comes from, but it does come from an application of the Schrödinger, Houston, Joseph, Wouter's theorem, if for anyone who knows about that. Okay, so this is really nice. It says this is an if and only if condition, right? If I can find positive rates such that this equation is satisfied, then I know that there is some way that I can physically realize this ensemble. And it may have to be adaptive, but I don't need to get into those details. I just know that it is possible. And it is certainly the case that in general it does have to be adaptive. Yeah, so the interesting thing is for most, or for a typical master equation, there are many ensembles that represent rho are not going to be physically realizable. And in particular, the diagonal ensemble, the one which has, so if I have a d-dimensional system, there's always going to be a diagonal ensemble with just d states, which represents the system. But typically, that is not a physically realizable ensemble. Okay, so this was the question then. So do we attacked in 2011? So let's say we have a d-dimensional system with a Markovian ergodic evolution described by this master equation, and we want to know. Well, let's see. All right, so this is a recap. Sorry. Okay, so an ensemble is physically realizable if there exists rates such that this equation is satisfied. The question is, given a master equation, what is the smallest possible k, which we'll call k min? How big a brain do I need to track the state of this system? So what we did in this paper is, well, one of the things we did is to just attack this with a counting argument. So the number of real parameters in this problem, if we're just going out to look for solutions to these equations, right? So I have k states. Each state, pure state, has 2d minus 2 real parameters, and these rates, there are k squared minus k of them, because the diagonal ones don't matter. And so that's the total number of unknowns is this. And if I look at this equation and say, well, how many constraints does this equation imply? It's k into d squared minus 1, because I've got k equations, because this is for all j. And each one of them is to do with a matrix in Hilbert space, but that matrix is automatically Hermitian and traceless. So that reduces 2d squared to d squared minus 1. Okay, so if you just say, well, then when do I have more unknowns than constraints, which is when I'd expect to be able to get solutions, the answer is this. So when k, okay, maybe I won't, yeah. Roughly, for large d, k has to be bigger than d squared. Okay? So this is different from the classical case. In the classical case, as I said, if you have a D-level system, you only need D states to keep track of it. A brain the size D. Whereas for quantum systems, this argument suggests that you need quadratically many, or a quadratically bigger brain to do this. Now, okay, can we prove this? Well, it turns out this is actually an incredibly difficult problem to solve this in particular cases, because it's an example of an NP-complete problem with large D, and even for small d, it's surprisingly difficult. However, well, no, okay, let's go for the first case. So to begin with, we'll restrict to D equals 2, so just a 2-level atom. And then it's convenient to use the block representation, so I'll use R to represent my states, the block vector. Then the master equation then looks like this equation here, just a linear equation in R. And if this is going to have a steady state, we're going to require A to be correspond to a stable evolution. So that's called a Hurwitz matrix. So all of its eigenvalues have a negative real part. And yeah, so the steady state then exists. Right? And what we seek is a physically realizable ensemble of pure states described by these R. So in other words, we need these rates and we need K of these vectors, which have to be pure. So that's this quadratic constraint. And they have to say, this is what the equation that I wrote before reduces to for the case of that. So this is still a pretty difficult problem. I've got 4K quadratic equations in K squared plus 2K unknowns. And again, this is still for large K, this is an NP-complete problem in scaling in terms of how it scales with K. But you might notice, and maybe I'll just do this on the board, if I restrict to just K equals 2, so this is just to make sure that this is actually a tutorial, right? I'm going to do a problem on the board, right? For K equals 2, I just have 2 equations. So one is that A is a matrix. Sorry, I hope everybody picked that up, right? And B is a vector. So AR1 plus B equals. So what do I want to do? I want to do K. Let's see, so K12, no, so K11, but K11 is 0, so I don't need to worry about that. So K12, R2 minus R1, so that's the only non-zero equation I get from that. And then for R2, I have AR2 plus B equals kappa 2, 1 into R1 minus R2. And if you look at this equation, if you subtract these two equations, the B's cancel out, and I get A into R1 minus R2 equals kappa 1, 2. Well, let's put it the other way around. Yeah, oh, all right. Yeah. I'll swap the order around. Okay, I get this, which is now just a linear equation. Okay, and it's, in fact, it's an eigenvalue. Well, okay, it's not linear, it's a quadratic equation because there are unknowns, right? This is unknown and this is unknown. So it still looks like a quadratic equation, but this is just an eigenvalue equation, okay? And we know how to solve eigenvalue equations. So what it's saying is that if I can find an eigenvalue for A, then, so that's that equation there. A real eigenvalue for A, then, yeah, maybe I'll say what this means. It means the difference between, if there exists an eigenvalue for A, then, eigenvector, sorry, for A, let's say that my rho steady state is here, so that's my R steady state, which is inside the block sphere. And let's say that there's an eigenvector for A, which is in this direction, then I can simply project it to the surface of the block sphere like that, and call this R1 and this R2, and you see that they will then satisfy this equation for some choice of kappa 1 and kappa 2. Okay, because the difference between them is solving the eigenvalue equation. And so, yeah, that's what this these equations here are saying. I can work out everything explicitly. And I should say, right, because this is the 3x3 matrix which is stable, there is guaranteed to be at least one real negative eigenvalue. So this is always going to work for any two-level system dynamics. So it doesn't matter what the master equation looks like, how many jump operators there is always a solution for a two-level system, a qubit, in terms of two possible states. And so here's an example. So my favorite example, always resonance fluorescence, so a damped atom with driving. So this is just a picture of the master equation evolution. If I just start at some pure state, the master equation evolution takes me towards a steady state which is internal to the Bloch sphere, it's on the the x equals 0 plane. Right? In this case, what am I saying here? Right, so A has an eigenvalue, eigenvector. One of the eigenvectors of A with an eigenvalue of -1/2 is just a vector in the x direction. Okay. And so what that means is there's always going to be a solution to the equation, right, that we're looking for, a physically realized ensemble, which is just the steady state, because it's all symmetric, plus or minus some constant times a vector in the x direction. So what that looks like for small driving, right, everything is down here. It's a bit hard to see what's going on. As the driving gets bigger, the steady state gets less pure, but it's always just the steady state and two vectors either side in the x direction. And for very high driving, so this is ohms equals 5, they get towards the being orthogonal, but they're never actually orthogonal. So these are two non-orthogonal pure states that I know I can force the system to jump in between by doing some appropriate measurement on the path, and it will actually be an adaptive measurement. Okay, so it also turns out there are other solutions. So if the driving is small enough, and you get more real eigenvectors, and that means that there are other two-state ensembles, and so that's an example of another one. And we can also do weird things. We can find ensembles with 3 elements, for example, and I guess this is going to be relevant to next week's talk. So you can start to do interesting things like break the symmetry. So the Liouvillean is completely symmetric in the YZ plane, and these ensembles respected that symmetry in the sense you can see that these mirror images of the other, and these ones, they're both in that plane, but if I go to more than 2, I can get things which actually break the symmetry of the dynamics. Because one of them is off-center and the other is off-center. And this one is, the big population is off-center in the other way. Okay, you might wonder so I've assumed perfect measurements and everything, but you might still wonder, well, okay, the theorem says that these exist, but are they stable? Like if I actually realize the adaptive measurement, and I guess I'm getting ahead of myself, we can find, for all of these simple cases, we can explicitly find the adaptive measurements that are required to make these jumps happen, to make the system jump between these between these states. And I do want to stress that it is only ever in these states. So it's not as if it jumps to this state and then moves around, and then when you get another jump, it jumps to the other state. No, it's in this state and it stays there forever. Just like in the Einstein-Bohr picture, until you get another jump and then it jumps over here and it stays there until it jumps again. So we get back that simple picture of, jump somewhere and stay until we get another jump, but they're not orthogonal states, and we can, it's much more complicated than other ways. But as I said, so we can actually find the adaptive measurements that we need to make for these. And so I was interested in the question of, is it really stable? If you deviate a little from there, maybe the whole thing just goes haywire? But no, it turns out that they're incredibly stable. So we proved analytically that for all of the examples, the particular examples we found, we proved that they were asymptotically stable in the sense that the expected overlap with one of the states you want is always going to go to 1. But it's sort of interesting the way it gets there. You can have some of the, you have stages, and some of these stages are actually, so this is the fidelity with the closest state. So the fidelity can actually decrease, but then you get a jump and it goes up to, it's so close to 1. Sometimes a jump can actually cause, you can see a tiny little decrease in the fidelity for a jump there. But this simulation, we've essentially forced it to be extremely unlikely, the sequence of jumps, in order to show these things. If you just look at a typical trajectory, it's incredibly boring. It looks like this. Essentially, almost immediately, the system goes into one of those states, and it never comes out. So it's very nice stability properties in that way. Okay, so that's the answer for a qubit, right? So for a qubit, we've proven that a 2-state classical memory is all that it takes. But we had the original thing, which I told you, was that the counting argument suggested that actually, in terms of D, it would be bigger than D in general, right? Well, I'll put it back. Right, so this was the original counting argument which we had in the 2011 paper, was that the K-min you'd expect to be D minus 1 squared plus 1. And so if you put in D equals 2, this gives you 2, which is consistent with what we found, okay? But for larger D, this suggests, so as soon as you have D equals 3, for example, that's 2 squared, which is 4, plus 1 is 5. So that would suggest for a 3-level system, you would only, in general, expect solutions with jumping between 5 states. So in other words, more states than you have dimensions in your system, and the larger D gets, it grows quadratically. Now, it turned out that this was not quite the full story. So with my student in 2019, we re-looked at this in terms of, does it depend on things like the number of Lindblad operators? And it turns out, yes, it does. And so there's a correction to the original Karasik-Wiseman formula. But it doesn't really make much difference to the story. It's still a quadratic scaling. So yeah, doesn't matter too much. We also, in one of the papers in that year, we looked at having dynamical symmetries, which can reduce this. So there are reasons that it may be smaller than you'd otherwise expect. Okay, how are we? So this is the main question which we were interested in, was can we actually prove that you need a number of states which is bigger than the dimension of the system, because that would prove that there's a gap between the classical and the quantum case. Because in the classical case, a D level brain is enough to track a D level system. So that's the main one. We wanted to really check a new theory against the old theory, and we wanted to check our new theory as much as possible. I think I won't go through all of these details, but maybe I will give the answer one, because that's sort of the most important. So we can say, yes, there are master equations for which we can prove that you need a brain bigger than the size of the system, so to speak, where the minimum number of states that the system could be jumping between is more than the dimension of the system. So another way you could put it is open quantum systems are generically harder to track than open classical systems. So we did this essentially by, we did this numerically, but numerically in the sense of doing some very fancy mathematics to prove the infeasibility of solving these equations. So it wasn't just like, oh, we tried hard and we couldn't find any solutions. No, we proved that no solutions existed, and therefore we know that, yes, it's K in general has to be bigger than D. Okay, we then did some other work which showed that our refined parameter counting was better than the original one, so that was supported. And even more, blah, blah. We found that our refined parameter counting is supported. But I guess it's complicated because it's ridiculous. Like originally quantum trajectories were meant to make simulations easier, right? That was the idea. You know, you had these systems, high dimensional quantum systems, which couldn't be solved on a computer. And so because the master equation wouldn't fit, and so therefore you use quantum trajectories to make it easier. And now here we are 30 years, or whenever, 25 years later, and we're considering a 3-dimensional quantum system and spending 8 hours on a supercomputer to try to prove something about quantum trajectories. So I find that sort of ironic that we can take something simple and beautiful and make it incredibly complicated. Okay, so yes, these are exponentially hard problems to solve, but nevertheless, the best we could do by simplifying as much as possible is that we think our parameter counting argument works. Okay, so that gets me to my conclusion. So adaptive measurements for profit. Adaptive measurements are a type of measurement-based control, but it's distinct from feedback, and it has no analog classically, at least for perfect measurements. And they have countless quantum applications, and many of them have been demonstrated experimentally. So a lot of the examples I talked about were in terms of phase estimation. So there are all these different varieties of phase estimation, depending on interferometric, coherent state, squeeze state, static phase, changing phase, any number of varieties you could look like, but yeah, a lot of experiments have been done. Other examples of state discrimination, with a fixed number of non-orthogonal states, so identically prepared but non-orthogonal, and the other example of measurement-based computing, and then getting on to this one, the adaptive measurements for pleasure, which I've talked about. So yeah, okay. You probably remember all this. I've said it enough times. For a classical system, you can keep track of the system with as many states as the system has states, but for an ergodic quantum system, generically, you need quadratically many states, a memory quadratically bigger than the number of levels of or the dimension of your system, and you need to use adaptive monitoring schemes in order to be able to realize these pure state ensembles. Right, special cases for a qubit, one classical bit is always sufficient, but even for d equals 3, we've proven that k equals 3 is not sufficient. So yeah, you need a bigger brain to do quantum physics. Okay, thank you.
Thank you for the excellent lecture. Now is the time for questions. Then maybe I can ask one. So in the case of the diffusive measurement, you showed that the variance could be reduced by 50%.
So this is back with one of the very early, sorry, this talk or the previous talk?
Part of the adaptive.
Okay, part of the adaptive. So maybe it was the very first example which I gave for phase.
I was just wondering, since it's a very simple number, is there a simple reason for this reduction?
Yeah, okay, that's a good question. Yes, okay, there is. So this is the, so I'm given a coherent state. So this is a representation in phase space of that with an unknown phase. So how do I try to estimate that phase? So the standard way is to do heterodyne measurement, which is equivalent to measuring both quadratures, so say x and y. But of course, you can't measure them both equally well. So it's actually equivalent to, so heterodyne measurement is equivalent to splitting the coherent state and putting half of it into, or splitting your signal and putting half of it into an x measurement, half of it into a y measurement. So if you think about that, that's approximately like what you've done now is, you've reduced, so let's see, we've reduced our amplitude, yes, so this is meant to be on the same scale, so you've now got two smaller coherent states, and on this one I'm going to measure x, and on this one I'm going to measure y, and then roughly you could say, yeah, and I'm going to take, arctan of y over x or whatever it is. I mean, you don't actually do that, but classically you just do that to get an estimate of the phase. Okay. So why is this? Yeah, so this is a bad thing to do because, yeah, if you think about if I take the coherent state and reduce its amplitude like that, the intrinsic phase uncertainty of this one is bigger than the original one. So the measurements that I'm doing here are going to be, to infer the phase, are going to be worse. Okay. Whereas if you, here's my original state. If I were able to measure this quadrature, I'll just call it quadrature Q, I could get an estimate of the phase very well. Because I'm measuring this one with 100%, and if I think of this as moving a little bit, essentially that just moves me up and back this way, so I'm able to estimate the phase from that. So the idea of the adaptive measurement is exactly to wiggle around your local oscillator until you're measuring as much as possible along this direction. And so so for a large coherent state, it turns out you can spend almost all your time measuring what you want to measure. Okay, so the 50% is exactly because the 50% intensity loss which you get here gives you twice as much phase variance in the heterodyne measurement. So some people talk about this as like adding 1 photon worth of noise or something like that. But essentially it's like, yes, if you do a heterodyne measurement on your coherent state, it's as if you've increased the blob more before you've made your measurement.
Thank you.
Hi, so I think I missed something. When you spoke about the symmetry of the PREs, and then sometimes you can increase K and you break the symmetry. Were you talking about this? This is independent of any symmetry of the actual master equation?
So the independent of it. I mean, so you only expect to get symmetric solutions when there is a symmetry in the master equation.
Okay.
So here's a case where the master. So we wrote a whole paper which is written in the language of symmetry groups. So if you're really interested in symmetries of master equations and physically realizable ensembles, then I can point you to that. So I'll probably get the language wrong here, but essentially the master equation has a mirror symmetry here because just the form of it here. So if I how's that going to work? I don't quite know. I can't, because I'd mess up the commutation. I can't say I'll replace X by sigma X because the commutation relations don't work then, but you get the idea?
Yeah, I'm happy with the symmetry of this master equation. I just wondered what the intuition was as to why the symmetry is broken when you increase K.
Oh, so it isn't necessarily. It's just that we can force asymmetric solutions when we increase K. So yes, so I had a picture in fact of one and then I took it off. So there also will exist symmetric solutions, but like it's not as if we completely characterized this or anything, because as I said, even for 3, like the equations are getting quite involved to solve.
Any more questions?
Hello, this is more of a curiosity. I know that there are some results in which people have proved that you can simulate a classical stochastic process using less memory if you use a quantum system for the simulation. Is there any relation with these results?
Yeah, that's a great question. I think there is a relationship. And I've had this idea for many years and never got around to writing it up. Back to this picture. So you're talking about the work on like quantum epsilon machines, is that right? That sort of work? Yes. Yeah. So essentially I could think of, so if I think of a discrete time version of this, and I should say that like everything that I talked about here again works in discrete time as well. But again, we haven't actually published that, but we know that it does work. And the number of constraints and unknowns is the same. So all the same, essentially all the same things hold. The idea of that they have of simulating a classical stochastic process is to have a detector here which gives outputs, which is the classical stochastic process you want. And they care about having this quantum system having the smallest possible dimension. Yes. So what's different here is making it adaptive and actually making what your detector detects from the quantum output. So you could think of this as a quantum machine, which is outputting a quantum, I don't know, it outputs a quantum something. It has a quantum output. In the epsilon machine, the complexity work, yes, you just immediately measure that in the fixed basis. Whereas here, yeah, interestingly, you've got a quantum machine here, but in this version, you have a quantum machine hooked up to a classical machine, and you're actually trying to minimize the memory that this classical machine is using to keep track of the quantum machine. So I do think that there's a pretty close relationship there, but it's not the same thing precisely because we make this adaptive. Yeah.
Then I believe it's time for the tea break.
Cool.
We convene in 20 minutes.